The education of a laboratory scientist. Once upon a time, students were invited to hear or read about experiments or watch newsreels of famous scientists doing strange but important things which unlocked the mysteries of the universe. And then one day, classrooms of students were shown the mysteries of said experiments by watching demonstrations of dissections and experiments in the lecture hall, hence the extant sinks in Slater and Ryan lecture halls. Eventually, the students were actually invited to conduct hands-on scientific experiments following step-by-step procedures. Doing is better than simply seeing. This level of experimentation developed essential laboratory skills among a relatively large number of students in a given semester. Maybe 18 students times 2 to 8 lab sections per semester. It remains an excellent, efficient method for science education in 100 and 200 level laboratory courses. However, the theoretical understanding of the experimental method is limited to what appears in the introductory paragraphs of the laboratory course manual and what can be provided in a 10 to 20 minute pre-lab lecture. Consider next what happens when an aspiring science student graduates only to have a laboratory supervisor who asks that he or she conduct an experiment for which an A to Z step-by-step instructions and 100% relevant background information is not neatly contained in any of the laboratory manuals or any of the courses he or she has taken. Perhaps it would be easier if the student had previously been challenged to both plan and conduct the steps of a scientific experiment. And this is exactly what I asked them to do in my molecular biology laboratory course. Students are charged with cloning a specific gene, but they are not given step-by-step, microliter by microliter, incubation by incubation instructions for accomplishing this goal. In short, I ask students to learn how to do their experiments before they do their experiments. This, of course, takes time. It takes time away from the precious few hours in which to actually conduct the steps of the experiment, and yet if I were to shortcut the laboratory to get more done and actually tell them exactly how to do each step, they would lose about 70% of the capability they could and probably should learn as a laboratory scientist before they graduate. How then might I shift some of this designing and planning to a time and space outside the lab? Before we start the experimental steps of each section, I coach students through the what if and well then what problem solving and planning within the laboratory class itself. This has to be done before they can proceed with the wet lab work of the day. Here's what students have as resources. They have an assigned text on gene cloning, which explains the theoretical background for most common methods in gene cloning. They also have reference volumes and catalogs in our lab, which I use and teach them how to use to find basic recipes and protocols. I require that they collect all of this information to do every step of their gene cloning project into what is commonly called a protocol binder. They now have a choice of how to organize this material, but I have always recommended up until this point a 3-ring hard copy binder. But why should students organize essential information for their cloning project in a hard copy 3-ring binder when more and more classical reference materials are available electronically? Linked cartoon animations remain a highly expedient way to teach theory of what should be taking place in a test tube, molecule by molecule. For example, the polymerase chain reaction animation, which is actually linked to in this wiki space. Another reason is that biotech companies now publish nearly all of their technical bulletins for the reagents we use exclusively online. Try getting a hard copy. This allows for inexpensive distribution and instant revision when necessary, and website maintenance pays dividends, of course, by increasing the technical confidence of users who are thinking of using their products, and most importantly, it reduces demands on technical support. An example of this is shown in the underlined link for Fusion PCR polymerase, which is sold by New England Biolabs, right in Ipswich, Massachusetts. Additionally, some academic research labs post highly specific information about the methods they use or develop in their own lab. Educators post a vast array of podcasts and PowerPoint presentations which teach the background of many methods, and they also post these, oddly enough, for free. Each semester, students themselves seem to come to me with new, cool tools that they have actually found which teach them a little bit about the experimental methods they will be using in the lab. They're usually pretty excited about these discoveries, which in turn lead others to do likewise, like myself and a few other enterprising students. Funny enough, approximately 80% of the new learning resources brought to me by students in the last 3 years have been electronic. So what does this tell me? Electronic is where they look for information, because they're too lazy to go to the car to actually get their textbook, and of course it's not all there anyway. Electronic is where they can now find high-quality information. Electronic is where they spend their time for work and for play. Electronic is one space where they already organize their social networks. Electronic is where they could be building a set of resources for their own lab class and lab classes to come if I give them a place to organize it. If it's not them, eventually it will probably have to be me. I prefer that it's them. And last but not least, the number one reason that laboratory protocols to plan the students' experiments should be organized electronically is the Journal of Visualized Experiments. Let me ask you, how effective are written instructions for anything even remotely technical like assembling furniture? How much better would the video be? Over the years, scores of scientists have been able to repeat experiments performed by another laboratory precisely due to the inadequate medium of communication. At their wits' end, many a postdoc and graduate student have traveled to another lab spending weeks learning a new technique only to find out that there was only one teeny little step they were doing wrong which cost them months of frustrated attempts. The Journal of Visualized Experiments could be the end of many such frustrated endeavors. High-quality, highly specialized, peer-reviewed method videos. And let's hope there are plenty of those out there already posted on this website to be used by my students before they come into the lab. The idea is to have students actually be thinking about and planning these experiments before they come in the lab. And of course, for me to set some things for them to do, some problems to solve. My assessment plans are such. Normally, I give a midterm and a final in the laboratory itself, in addition to the assessments that we do in the lecture, which are largely more to do with the actual facts of molecular biology as opposed to the experimental methods. So in the midterm laboratory and final exam, they often have to solve problems. They're often given data sets they have to analyze, and of course they have to plan mock experiments. I could, for instance, after using OhiSpace or some other collaborative space this spring semester, compare the performance of my students on their midterm and final exam with those of the last 3 years' worth of students for which such a tool has not been available. Those students in previous semesters were required to keep a paper copy of their protocol binder. This semester, it would be interesting to experiment with students who choose to have an electronic protocol binder themselves and those who have hard copy, and for everyone to be contributing to the electronic space as and when they see fit. That's the plan, and this is my video.